All right. So we can break this sum into two parts. We've got the 2 to the n plus 1 becomes 2 times 2 to the n, and then the 2 to the n can go over the 7 to the n. So our a is 2 and r is 2 sevenths. So r is 2 sevenths. Absolute value is less than 1. It converges. So then we want to find the sum. We're starting at 1. So that is AR over 1 minus R. So A is equal to 2. R is 2 sevenths. Plug it all in and solve. So let's see, we've got 4 sevenths all over 5 sevenths, or 4 fifths. That would turn out to be. So still not that bad. And we're going to need to use that trick quite often for these types of problems, where we're going to take something to a power and break it into its individual parts. So here's one that's similar. 1 to the n plus 1, 1 to the n minus 1. So I can rewrite this. Not in the glare, right? Okay. So that's e to the n times e to the first. And this is pi to the n times pi to the minus 1. The pi to the minus 1 can go up in the numerator, and I can pull out an e pi. And then I've got e over pi to the n. So my a is e pi, my r is e over pi. So is the absolute value of e over pi less than 1? Well, that's correct, because this is 2.7 and that's 3.4 roughly. So that number will be less than 1. Converges. And let's instead have this one start at 0. So the sum then is a, which is pi e, all over 1 minus r, e over pi. And the only thing you can really do to clean that up is to maybe multiply everything by pi. So this would be pi squared e, pi minus e. So again, this is all about manipulating the functions. Alright, so I think we have two more here. First one is 3 to the 2n times 2 to the 2 minus n. So this one's a little different. We actually have to make this 3 to the 2n into 3 squared to the n. And we do that because we want something to the n power. Then the 2, we can make 2 squared times 2 to the minus n. So this is 9 to the n, and that power there that's minus n, we could put that in the denominator. And then 2 squared is 4. So A and R, we need the absolute value of R. Well, in this case, it's greater than 1. So we can stop here. This diverges. And therefore, we cannot find the sum. All right, let's go ahead and do this last one. So that one there, I'm going to break into 2 separate sums. So this is going to be over 7 to the n minus another sum, which will be 4 over 7 to the n. I will then test both of these individually. If they both converge, I'll find both of their sums and then take this one away. If one of them diverges, the problem ends. Because if one portion of the original sum diverges, so does the original sum. Now it turns out in this case, both of these values for R are less than 1. So both of these are going to converge. Which means I have to find the sum for each one of them. The sum for this first one would be 5/7 all over 1 minus 5/7. Now it's technically AR up top, but A here is 1, and so is in this problem. And I would subtract this sum, 4/7 over 1 minus 4/7. So that's going to be so it's like 5/2 minus 4/3. So that's going to be 15 minus 8 all over 6. So that's what, 7/6? think that's all of geometric series. So we can now look at telescoping or collapsing. Now these are called telescoping or collapsing because you're going to see that a lot of terms tend to cancel out. And it says that here that almost all the inner terms are opposites and hence cancel. So first what we need to do is we need to find the limit of the sequence, the infinite limit. And if it approaches 0, then we can continue. And then the next thing is to take the partial fraction decomposition. So let's go ahead and try one. So first thing I have to do is take the limit of this. So I need the limit as n approaches infinity, 1 over n times n minus 1. That's pretty straightforward. If I plugged infinity down here, right, I'd get 1 over infinity, and that's 0. So that's good news. That means I can continue. Or maybe to you it's bad news because you have to keep going. So we're going to do partial fraction decomposition now. So I've got two linear distinct terms here. So this is going to be a over n plus b over n minus 1. And that combination has to equal 1 over n times n minus 1. Okay. So if I do my cross multiplication here and set just the numerators equal, I would have a times n minus 1 plus b times n all equaling 1. Right, because I would multiply a by this, b by that. That's going to give me a plus b times n, or a plus b has to be 0 because there are no n terms on the right. Then I have minus a must equal 1. So that right off the bat tells me a is minus 1. And if a is negative 1 and we have to add something to it to get 0, well then b is positive 1. So we have a and b right off the bat. We're going to replace them and put them inside of the summation. So I've now got the sum. We've got minus 1 over n plus 1 over n minus 1. So let's start plugging in 2 and see what the terms look like. So the first terms would be minus 1/2. If I plug 2 there, I get 1 over 1. Plus, now the next number would be 3. So plug that in. So we get minus 1/3. And then we would get plus 1/2. Let's do at least one more. Plug in n equal 4. So minus 1/4 plus 1/3. And let's go one more. That would be 1/5 negative plus 1/4. And then just continue. So let's look at the terms. I've got minus 1/2 plus 1/2. I've got minus 1/3 plus 1/3. Minus 1/4 plus 1/4. Well, you can guess that this negative 1/5 is going to cancel with the next term. And all the terms will do that out to infinity. So the only thing left is this 1 here. So this tells me that it's a convergent series. And this is my sum. Any questions about that? Why is it minus 1 over n instead of plus 1? So I took this and decomposed to these two, and a was negative 1. Does that answer your question? If not, I have one more to do. Hopefully that'll clear it up for you. Okay. So let me do one more and see if that helps. So I've got 5 over n squared minus 7n plus 12. So first, we would want to try and factor that. So I've got two numbers that multiply to 12, add to negative 7. Minus 3 and minus 4 should do that for us. Which means, again, I have two linear distinct factors. So I should get a over the first one plus b over the second. So again, multiply this plus that, and it must equal 5. So I'll multiply it all out this time, maybe that'll help. Then I'm going to add the x terms together. And add the constant terms. So there are no x terms on the right. That means that a plus b must be 0. And this guy, minus 4a minus 3b, has to equal 5. And I realized before we started doing all this, we should have taken the limit, right? Limit as n goes to infinity, because if this thing doesn't converge, there's no sense in doing it. And thankfully it's quite easy to show that that goes to 0. So yes, I just did the limit, sorry about that. Alright, so that means it's convergent, which means there's reason to do this in the first place. Now, I got a system of equations here. I notice all these are negative and all these are positive. So rather than solve for one and plug in, I'm going to cancel. I'm going to multiply this first equation by 3 and add it to this second one. So this would be 3a plus 3b equals 0 if I multiply the first equation by 3. And then adding these two, I would get minus a, the b's would cancel, and I would get 5, which means a equals negative 5. And if a is negative 5 and a plus b must be 0, b has to be positive 5. So now I'm going to take those, plug them in over here. And then I want to start substituting in the values of n to see what the terms look like. So my first term, when n is 5, I get minus 5 over, plug 5 in here, you get 2. And then we get plus 5 over 1. Plus. Now plug in n equals 6. So 6 minus 3. And then the next one is 6 minus 4. Let's go ahead and do another one. Plug in n equals 7. And we can do this all day long. 3 is usually enough to see the pattern. So I've got minus 5 halves, plus 5 halves, minus 5 thirds, plus 5 thirds. And again, you can anticipate that this is going to cancel with the next term. All left behind is 5. So again, this tells us it's convergent or converges, and this is our sum. So I'll pause for a second. Does anybody have any questions? think I understand this. You make it sound like you didn't understand stuff before. Alright, so it looks like a decent amount of people are saying they're good. So I'm going to go ahead and erase this guy. What will the limit be if it is divergent? Anything other than 0. So it could be 2. And I might suggest going ahead and starting to make your note card as we go through these. Right, so we have geometric, you got to have AR form, and then you got to have R, absolute value of R less than 1. You could write yourself something about telescoping. All right, you got to take the limit. If it gives you 0, it converges. Things like that. Alright, so let me close this. And pull up the next section. Okay. So, when are you posting the grades for the exam? I'm going to try and get them done this weekend. Alright, so far we've learned what is a sequence. We talked about the definition of the infinite series, and then we looked at geometric and telescoping. Those are the two ones that we know of so far that you can find the sum. All of the ones that we do today, the sum is going to be not important. We just want to know, does it converge or diverge? So the first thing here is called test for divergence. And that is very simple. It's somewhat powerful, but at the same time, it's only one-sided. So when it's called test for divergence, it literally means you can only tell if something diverges. So notice it says here, if the limit as n approaches infinity of a sub n does not exist, or the limit as n approaches infinity is non-zero, then the series diverges. Maybe a better statement to remember is that it says that if the limit gives you back 0, it does not mean it converges, and the next bullet tells you another test must be used. So, let me say that one more time. Test for divergence is just taking the limit as n approaches infinity of a sub n. If you get back 0, the test is inconclusive, and you must use another test. Now, as of right now, we don't have enough of them in our tool bag to be able to choose another one. But on the test, for instance, you run into that situation, you'd have to try something else. If it gives you anything, infinity, -5, 12, pi, whatever, anything other than 0, we can automatically say it diverges. So let's go ahead and try some of these. So this first one is 2 over n squared plus 2n minus 3. So again, I just want to take the limit as n approaches infinity. And this one should be pretty straightforward to you. If I plug infinity in down here, all those things are going to be getting really big or infinite. And so this limit gets me 0. So right off the bat, I found one that's inconclusive. So as I said, if we had more tests, we could go ahead and try another one. This one we could technically do the telescoping, right? It looks like it might be a telescoping series. And I can tell that because it looks like it's factorable down here, which means I can do partial fractions. So keep that in mind as you're going through these as to how can I tell a series is a certain type. All right, let's do this one. So again, I want the limit as n approaches infinity. 2n squared plus 3n all over the square root of n to the 4th minus 5n minus 1. So every term here, I want to divide by the highest power of n in the denominator. Well, I have n to the 4th, but it's to the square root. So square root of n to the 4th is really like n squared. So up here I'm dividing by n squared, and down here I'm dividing by n to the 4th under the radical. And that's because of this. Right, these two things are equal. N squared equals the square root of n to the 4th. All right. So I'm going to have 2 plus 3 over n on the top because I divided by n squared everywhere. All right, so I did n squared, and then down here I'm dividing everything by n to the 4th. So this becomes 1 minus 5 over n cubed minus 1 over n to the 4th. So now, recall the fact that the limit is n approaches infinity of 1 over x, so let's make this x, to the r equals 0 for r greater than 0. And if that's the case, then this guy, and this guy are all going to go to 0. So this time I got something that was non-zero. I got 2 out of it. That means I can say that this is a divergent series, or it diverges. So by test of divergence, this series diverges. So I'm going to keep rolling along. If you have questions, post them up here and I'll answer them. The next one is this arctan. So we would take the limit as n approaches infinity of arctan. Now we may not know what happens to that function as n approaches infinity. So what I suggest is graphing it. If we do that, arctan looks something like this. Oops, gotta go through the origin there. And it has an asymptote atop and one on the bottom. And these occur at pi over 2 and minus pi over 2. So it says, thought when you take the limit and you get a number, it converges. Now that is for the sequence. So this is test for divergence for an infinite series. So it has its different set of rules. So it said, let me just scroll back up real quick. It says up here, see if I can get it out. So it says if the limit does not exist or is non-zero, series diverges. If it is zero, we can't say anything. It's inconclusive. So this one here, we got a number which is non-zero, so it diverges. This one was zero, that's inconclusive. And then this one, so as I was saying, the limit as n approaches infinity. So n getting big would be this. We're approaching pi over 2. Again, that is some tangible number. Right? It's not 0. So this diverges. And the last one here, I need to take the limit as n approaches infinity. I'm going to rewrite that as 3 to the 1 over n. So that would be 3 to the 1 over infinity. 1 divided by infinity is 0. 3 to the 0 is 1. This also diverges. Any other questions about any of these before I move on? So yes, this is for infinite series only. All of the series we're going to deal with are going to be infinite series. Yep, no problem. Alright, so I'm going to go ahead and erase this guy. So I think the hardest part with series in general is just that there's so many rules. So I don't think it's super hard to pick out the type of series. I don't think it's hard to manipulate them. It's hard to remember what are the rules for that series. Now this is one that you might like. This is called the P series. I really got to figure out how to get this glare off of here. An infinite series is any series that goes to infinity. Yes, infinite series meaning that the upper bound is infinite. Alright, so P series are fun. The only thing is I don't want you to confuse them with geometric. So remember, geometric was a times r to the n. the P series is 1 over n to a power. If that power P, right, it's 1 over n to the P, if that power P, this is greater than 1, let me just move the thing here so you can see it better. So if P is greater than 1, then the P series converges. If P is less than or equal to 1, the series is divergent. And there's a very special case. So we've already included it here. It says when P is less than or equal to 1, but the equal to 1 case is called the harmonic series. That's a very special series, and you could be guaranteed to see it again somewhere. So it's just the sum from 1 to infinity of 1 over n, and you don't even have to tell me that that's a P series. You can call it harmonic, and therefore it diverges. So let's go ahead and try some of these and use these rules. So we're trying to find P, right? First we've got to get it in the form 1 over n to the P, and then once we have P, P has to be greater than 1. All right. First one is 5 over 4n to the 15. Well, that 5 over 4 has nothing to do with that summation. So if I wanted, I could bring it outside. So this is then in the correct format. It's 1 over n to a power, and that power is 15. So P equals 15. That number is greater than 1. This converges. My class yesterday, this was one of the first things we did, and they were saying, man, this is too easy. He must be doing this because it's April Fool's. So it is, for that one, it is that simple. The others are a little more difficult because we have to get them into the correct form. So this one here, we just need to, we can pull the pi out. Don't have to, but we can. And rewrite n to the 7/5 as the power. Once we've done that, we can identify P. That is 7/5. That is again greater than 1. Converge. So let me ask you guys this. Let me pull out the E here. How would you rewrite this one? That's n to the 0.4. So good, you would put it in the denominator and make it minus 0.4. So P there is a negative 0.4, which is less than 1. Therefore, this diverges. So yeah, you could write it as negative 2/5 as well. That works. All right. Part D. So I'm going to again take that and break it into 2. So this is now going to become 2/4 n cubed over n to the 2/7 plus this will be 3/4 So then I really care about what happens when I reduce these. So this would be 21/7 minus 2. So that reduces down to 1 over n to the 19/7. And the second one reduces down to so we've got, this is going to be 14 minus 2, or 1 over, sorry, this is minus 19/7, and this is minus 12/7. Alright, if I rewrite this one as sevenths, it's 21/7 minus 2/7. That's 19/7, but that would go in the numerator. So if I want to put it in the denominator, it becomes minus. So it turns out that this one right here, if I take p, it's minus 19/7, that's less than 1, that diverges. And technically, so does that one. But once again, if I break the original sum into 2 separate ones, and one of them diverges, the entire original sum also diverges. Is that clear to everybody? Okay. All right, with that said, thank you for answering. Can you decide how to rewrite this into a summation? So 1 over the n square root of n. So yes, this is the sum from n equal 1 to infinity, 1 over n square root of n, which we could rewrite. And let's make sure you see that. So plug 1 in here, you get 1 over 1 times 1, that's 1. Plug in 2, 1 over 2 times root 2. Plug in 3, right? So this works out just fine. N times root n is the same thing as n to the 3/2. So that again is a p-series where p equals 3/2. That's greater than 1. Therefore, converges. So I'm not sure. I think that's all of the examples I have for P series. Any questions about these before I erase the board? Okay. So again, not too bad, I hope. So the next thing is going to be the first time that we actually get to use calculus in these problems. Because we're going to do the integral test. So for the integral test, it says your function f must be positive, continuous, and decreasing from 1 to infinity, or wherever it begins. So if it's n equal 5 here, it must be from 5 to infinity. We then can take whatever a sub n is here, change all the n's to x's, and plug it into an integral. Now it says here if the integral is convergent, then so is the sum. Well, what does it mean for an integral to be convergent? Well, that is you get some number out of it. What is it for an integral to be divergent? Get infinity or negative infinity, or just flat out undefined or does not exist, that sort of stuff. Or if you get combinations of something like infinity minus infinity, that would be undefined. So all I have to do is take whatever's inside my summation, integrate it over the bounds that are given, and show that that thing either gives me some number or gives me infinity. So let's try those. So we just got done doing this one, the 5 over 4 n to the 15. And that was a P series, which we showed to be convergent. So let's now use the integral test to prove that it also works. So again, I can take my sum, translate it into an integral, and plug exactly a sub n in there, but instead of n, switch to x. Then as a technicality, I should be taking and changing this into an improper integral. Because I have an infinite bound. So I have to change from infinity to some c. I have to introduce a limit as c approaches infinity. I pulled the 5/4 all the way out in front. And now I want to go ahead and integrate this normally. So this is really x to the negative 15 in the numerator. I'd add 1 to that power and divide by the number. So that would be x to the minus 14 over minus 14, evaluated from 1 to c. So plug those in. would look like that. This first one here, as c approaches infinity, it's c to a negative power. So it's really like I need to put that down there and make it a positive power. And in that case, I'm dividing by infinity, which means all of this goes to 0. So I've really only got this term left. I've got 1 over negative 14, but that minus there makes it plus. So I end up with 5/4 times 1 over 14, or 5 over 56. So my integral returns some number. So the integral converges, and if it converges, so does the sum. So convergent integral, convergent sum. Let's try this second one. This would be limit c approaches infinity, integral 1 to c, 1 over x, natural log x, dx. This is a basic u substitution where I can let u equal natural log x. du is 1 over x dx. Is 5 over 56 what the sum converges to? No, that is not what the sum converges to. Not necessarily. So recall that I said that the only ones we're concerned about are geometric and telescoping for right now. All right. So if I make these substitutions, this is 1 over x dx, that's du, and then I have 1 over u. So I get du over u out of that. That's natural log of u. And if we plug plug u back in, it's also the natural log. And that's from 1 to c. So then we just substitute in those values. So when I plug in c, I still need the limit. Then I'd have minus natural log of the natural log of 1. So, natural log of infinity is infinity. Natural log of that is infinity again. Natural log of 1 is 0. Natural log of 0 is undefined, or if we thought about what the graph looked like, it's actually minus infinity. So I'm going to say does not exist, and therefore the integral and the sum diverge. All right, got one more of these guys. So any questions about this one? All right. So is it making sense, or am I going too fast and you guys don't know what to ask? So let's do this last one. So I need limit, c approaches infinity, integral 1 to c, and e to the n. Sorry, I need to make these x's. Keep doing that. And we need a dx. So that's integration by parts. We've done that quite a few times now. We would get x e to the x minus e to the x out of that. Evaluated from 1 to c. I'm going to rewrite that as limit c approaches infinity, e to the x times x minus 1, all evaluated from 1 to c, and then plug in. So this is limit c approaches infinity, e to the c times c minus 1 minus e to the first times 1 minus 1. So this term out here pretty easily goes to 0. So we're all depending on what this does. And I think we've had this discussion once before, but we've got e to the c times a linear function. So the question is, this limit, which one of these functions increases more quickly? And so we came to the conclusion that e to the c obviously does that. So it will dictate what the combination of these two do. So e to the c, when c goes to infinity, heads off towards infinity. So this whole thing gives us infinity, and therefore diverges. What do you mean, wouldn't it go to infinity either way? Yes, it would. But the other problem is, if you don't have that argument, you would get infinity times infinity, and then you have no idea what to do with it, right? I mean, you still get diverge, but you'd have maybe a little different reasoning. But I think you might get confused if you try to do the infinity times infinity argument. But yes, you can do it either way. So far today we have done, we finished up geometric series, we did telescoping series, we did divergence test, p-test, integral test. We've got one more set of problems to do, and then I will let you guys go. So this is asking us to estimate the sum of an infinite series to a specific area or error. So as we just did with the integral before, right, we could take a summation, an infinite one, and translate it and say it's approximately equal to an integral. And recall that integrals, as long as the function is continuous, can be broken into parts. So if there's some value n between 1 and infinity, I can make an integral that runs from 1 to n, and plus an integral that runs from n to infinity. I could then take the 1 to n integral and say that's going to be my approximation to the series. And this here is going to be my error. So we're going to call that sum, or that integral from n to infinity, the error. So let me try one of these and see if it makes sense. The steps say first you got to prove that it converges, because if it's not a convergent series, there's no point in continuing. Find how many terms n are necessary to ensure that the sum of the series is accurate to the given value, given right here in the problem. And then finally use Excel to find the sum. So first I've got the sum 1 over n to the 5th. What kind of series is that, guys? Right, that's a p series, good. So because it's p series, we can say p equals 5. So we first say p series where p equals 5, which is greater than 1, converges. So that's enough for part A to show that it converges. The next part says, now introduce an integral from n to infinity. So again, we need limit as c approaches infinity. Of this series. So 1 over x to the 5th dx. And it says it must be accurate to the 100,000th place. So we're going to say our error needs to be less than or equal to, we've got tens, hundreds, thousands, 10,000ths. The next one is the 100,000th place. You always go one more space and put a 5. So this is basically saying 5 decimal places, the accuracy. All right. Any questions about the setup before I go ahead and solve? Right, it's literally take the integral of this sequence inside the series from n to infinity, and it has to be less than or equal to whatever they tell you. All right, so let's go ahead and solve this. So I've got 1 over x to the fifth. That's really x to the minus 5. And so when I integrate that, I'm going to get x to the minus 4 over minus 4. And that runs from n to c. So let me just forget about that guy for a minute. Let's solve the integral. Plug in our bounds. I'm going to go ahead and pull the minus 1/4 all the way out front. And then this is now 1 over that quantity to the fourth. The limit as c approaches infinity makes this term go to 0. And so we're left with minus 1 over, well, it's negative times negative, so it's plus 1 over 4n to the fourth. And that has to be less than or equal to this decimal that I've come up with. So now I just got to do some algebra to solve for n. So I'm going to take this n to the fourth and I'm going to swap it with that decimal there. And if you don't believe me, then go ahead and do it in 2 steps and you'll get the same thing. This number is actually 50,000. And if I want n, I've got to take the fourth root of both sides. I think this comes out as 14.95 something. So it's either 14 or 15 terms. So, we've got that we need 14 or 15 terms to get an accuracy within 5 decimal places. That's what this problem tells us. So right, we started with an infinite sum, but we only care to get a number that's 5 decimal place accuracy. So we only need to calculate 14 to 15 terms. So any questions about that? I'm going to pull up the Excel file or an Excel file and show you exactly how this works. Alright, so you can see Excel here. So how about I put the information over here so we can see it. Alright, so my sum starts at 1. And then we can plug in any subsequent number, right? So 1, 2, 3, 4, 5, and so on. So let me just drag that now. Okay. Then my terms of my sequence are 1 divided by this number to the 5th power. Let's see if I can drag that and it'll cooperate. Nope. Oh, maybe it did. Yeah, we're good. Okay. So let me drag those. So that's each individual term. Now I want to do my sum. So this would equal the sum. No, you will not need to use Excel on the exam. It's just, this is a good way to demonstrate what we're doing. You can do a summation on your calculator, actually. Alright, so I want the sum. I want to do a running sum, so this will be the sum of the first term. And I'm going to put dollar signs in front of the letter and in front of the number. That will make it such that it always uses the first cell here as I continue on. So equals sum. And you should be able to hit F4 to do that. But for some reason mine was just turning down my volume yesterday. Maybe if I do function F4. There we go. Alright, so that automatically puts the dollar signs in, and then you're going to do colon. We choose this one. It looks like my dollar signs went away. There we go. Now let's see if I drag this, it'll calculate the sums. Nope, didn't like it yet. Okay. So equals sum. I need the first 3 terms. And I need this one to be that. Let's try this now. Still doesn't want to do it. Come on. Let me try just doing these. There we go. Okay, now let me go ahead and drag this whole column over this way so we can actually see the darn thing. Alright. And then let's bring this guy over, and then I'll erase the board. Alright. So what did we demonstrate? We said that we needed 14 or 15 terms approximately to get an accuracy of 5 decimal places. So what did we mean by that? Well, if I calculate the sum, I've done it here for, as you can see on the screen, up to 21. Notice, looking at the terms, and let me expand them slightly because I think they're only showing 5 decimal places, which means they're going to round on us. Okay, so looking at 13, 14, right, we're at 0.03692, 0.36922, 0.36923. So it looks like the first time that that 2 repeats is at the 14th term. And if we were to continue on forever, we would see that this term is accurate to 5 decimal places. So that remains a 2 if I kept going. He said, what was column N? N is just the individual terms plugged into the sum. So it was 1 over x to the 5th. I plugged in 1. Then the next one was plugging in 2 and plugging in 3. So if you will, that's the sequence. And then the other column was the actual summation. So the reason that this is interesting is that this stuff gets used in computer science quite a bit. And so you can run a calculation like this to determine how many terms you need in order to get an accuracy that you want. Or you don't always need to carry, 30 decimal places. So if you only need 5 decimal place accuracy, there's no point in calculating a sum that goes to infinity. Right? Computer time costs money. If you're doing really large calculations, it costs a lot of money because you got to have a supercomputer. So if you can discover that you only need 14 terms, and that's good enough, that's great. So there was one more example. I'm going to do it the basic way, and then, because I've thrown a lot at you, if you would like to see it done another way, I'll tell you to refer to the video from yesterday. And I'd also like you to try it on your own. So, if I integrate this guy, it would be the limit as c approaches infinity, integral n to c, plug in the function, all right, you would have to let u equal the natural log, du would equal 1 over x dx. So we'd have limit c approaches infinity, integral, this would be some a to b because we need arbitrary ones. We've got 1 over x dx, that's du, and then we'd have over u squared, or we can write it as u to the minus 2 du. You'd add 1 and divide by the number. So we get minus 1 over u out of that. Plug u in. It's natural log x. Evaluated from n to c. take a look at my notes here because it seems like I'm losing my mind here for a second. Okay. All right. Plug infinity in here. That's log of infinity. That's infinite. 1 over infinity is 0. So you end up with 1 over natural log n. Remember, the error has to be less than or equal to. This one says accurate to the ones place. So that's not even a decimal, right? Ones place meaning like 1, 2, 3. So you go one more and put a 0.5. So that's 2 less than or equal to natural log n. And then take e of both sides. So you get n is greater than or equal to e squared. So if I go to do this on Excel, right, e squared is approximately 7.38. So it's telling me I need about 7 terms. How did I get 2? 1 divided by 0.5 is 2. Move the log n to the other side. So it's saying about 7 terms. Now there's a problem here. So at the very beginning, we should have noticed that this sum starts at 1. Am I allowed to plug 1 into the natural log? I can, but I get 0. Which means I get divided by 0 here. So guess what? As it stands right now, this is a divergent series. So this tells me nothing for this series because it's divergent. And remember, I should have proven that it was convergent before I did this. So to do that, I would have taken the same integral, and I would have had the integral from 1 to n. So if I do that, this is going to come out as limit c approaches infinity. Sorry, I need no, 1 to infinity here. Ooh, losing it. All right, limit as c approaches infinity. I'd have minus 1 over log c plus 1 over log 1. This would still go to 0, but this would go to infinity. So that also tells me it diverges. So let me recap one more time. I knew that this was going to diverge. I jumped ahead to do this because I wanted to show you how to do that. However, I should have started with this integral, right? The integral from 1 to infinity. You got to prove this series converges. This isn't a p series like the one we did before. I can't do something simple. It's also not telescoping or geometric. So my really only option would be either test for divergence, but that doesn't help because I'm trying to show that it converges, or the integral test. So I did the integral test here, and it tells me that it diverges, which tells me that's no good. However, what I want you guys to do is start at 2. Reprove that to yourself. Go into Excel and prove that you get 7 terms. Now this time what you're going to see is it's going to be like 1.0 something, 1.2 something, 1.3 something, and I believe it's going to go up to like a 1.5. Now this digit's going to keep changing. However, I'm trying to be accurate to the ones place. So if this digit is above 5, it tells me to round to 2. And then it continues on forever. And that should be somewhere around 7 terms. So I'm sure there's some confusion there. So please ask questions. How did we get 5? This right here is a 0.5. It might be a little hard to see. I can barely see it on my screen. That's a 0.5. No need to be sorry. So yeah, because it says to go to the ones place, right, that's like 1, 2, 3. You always go one more place and put a 5. So I'll also go ahead and give you guys a quiz for the weekend, probably maybe 2 of them that I'd like you to complete. But they will not be due until Tuesday. So if you guys don't have any more questions, I'm going to go ahead and hold on, sorry. So first we test for divergence, then we do that work anyway to find the number of terms. So the idea is we have to prove that the series converges. If it converges, then we do this work. So I got ahead of myself. I did this first. I already knew that the series diverged. I should have started with that. Said that you would not continue, and then if instead the series started at 2, for instance, you'll see that it converges, and you can do this. Is that clear? Correct. If you get divergent, just stop. You don't continue solving.